Okay. This presentation I'm going to give is largely the same as it was when I presented it at the kickoff meeting for the cost action. It has a lot of ideas in it that I think are worth sharing with the larger group that's in the room today, and to remind people that we should be thinking about new things, new ways of doing things, ways of approaching some of the shortcomings of the brewer processing system. It would be really nice to talk about all this stuff, ozone, UV, AOD, UMCAR, NO2, SO2, but it's not going to happen in 15 minutes, and it's too much for me today. But I will talk about a few things. We have a number of outstanding issues. There are some very good stories about the brewer. A really properly operating one is giving us something on the order of 1% for a few hundred Dobson units, which is what the instrument is supposed to deliver. But we have some indication that it might be possible to get down to 1 Dobson unit as a result of comparisons between co-located instruments making measurements together. What are the outstanding issues? Well, we still have the outstanding ozone coefficient issue. A lot of people were kind of eager right now to adopt the recently published Raman cross-sections, but unfortunately, they're going back to the lab and doing a better job, and it's probably not wise for us to jump right in and change cross-sections right now, but rather wait until they publish their new results. We do need to do some of the back work, though, the infrastructure work, to understand how we're going to fit the database together and properly have a proper configuration control for all this stuff. It gets really complicated when you start reprocessing data. You've got to have 23 fingers pointing in all the different directions to make sure you really know what's coming out of your database. Stray light effects, I'm going to talk a little bit about that later in the talk. And the question of transfer of calibrations. If we actually go and reprocess data, then that fans out into a web of changes in all the other instruments, because if you change the calibration of your traveling standard, then all the instruments that it visited are going to have their data reprocessed. And anytime you've used an instrument as a comparison source, you're going to have to look at the implications in the data web that fans out from the primary calibration. And we still have to ask ourselves, for instruments in general, what is the right frequency for absolute calibration? The goal, I think, for UV measurements is to maintain a 1% accuracy in absolute irradiance in the field, which means being very careful, as Julian is, in taking traveling standards around sources and detectors in order to be able to make that level of performance available. The question there is, can we come up with universal standards? As far as I know, there's still a couple of % difference between what the Americans think the absolute irradiance is and what the Europeans think the absolute irradiance is. And so a goal of 1% becomes a little bit lame when that particular issue is still on the table. We have a lot of little things that sometimes are instrument dependent, like instrument number dependent. Things about wavelength stability, variations in the dispersion equation, improving the dispersion equation in individual instruments so that the wavelength calibrations out at long wavelengths are more precise. And the issue here is that comparison spectra may not be entirely reliable as well. One of the ones I use frequently for modeling is data from Kelly Chant's zero air mass extrapolation peak data. But there are positions in that spectrum where the spectrum cannot be properly extrapolated to zero air mass. And we still haven't done a direct cross-section comparison in a laboratory setting. What we're doing is going out and measuring the absolute cross-section as a function of wavelength, and then creating a differential cross-section with the unfortunate characteristic that if there's any inconsistencies between the values at different wavelengths, you're not going to get the right answer when you do the differential calculation. It would be very nice to have a brewer involved in laboratory measurements for a direct comparison of absolute and differential cross-sections. Comparisons during the TOMS 3F comparison and during the sonic comparisons in Zedanglia, clearly indicated the shortcomings of the single brewer and the Dobson in terms of stray light. Tommy and Esco have produced a very nice paper and put forward a correction scheme. From my approach, from my way of looking at it, I'm not completely happy that that's the best way to do it, and I'm putting forward a different method for taking a look at that. This is important because we've been changing from single brewers to double brewers at high latitudes, so we may actually be able to detect a positive trend in ozone, which is not due to real changes in the times of the year when we're forced to make measurements at very large ozone slant paths. It was already mentioned by John that we do have to tidy up the whole business of using brewers to do UV absolute absorption measurements to get aerosol dependence, wavelength dependence of aerosol absorption from the multiple slits in the brewer. And it may be that there is a possibility to actually combine operations or measurements from different model brewers. For instance, the Mark III measures in the UV and the blue, so we could get another set of wavelengths out of the blue part of the spectrum that could be used together with the UV absorption. Carl Mateer did yeoman service back in the 60s and 70s, adopting the Rogers optimal estimation method for UMCARE retrievals. And one of the things that was in there from the very beginning was the fact that it's possible to use multiple observations of the same thing. In other words, if you want a mean profile of ozone over a month, then you should just try to retrieve one profile that best fits all of the individual observations, because if you do that, the contribution of the a priori to the final answer goes down by root n, the number of observations that you're bringing together. And so that's a significant improvement in doing a monthly average, and Irina will probably be talking a little bit about that when she gives her talk. Brewer measurements, particularly the single brewer, fall off at large zenith angles. That's because sulfur dioxide is using a slit that's even shorter than the shortest ozone slit, so the effects of stray light are quite strong. And that was really discovered by comparing singles and doubles and seeing that the double worked out at longer path lengths of ozone and rarely scattering than the single brewers. And we haven't really addressed a way forward for handling that issue yet. So I'm going to talk a little bit about what I think is some progress in handling the stray light problem in a phenomenological manner for the single brewer. The idea here is that we know if we look at observations from Mauna Loa at very large ozone paths, we know that the curve falls off. And if we're capable of characterizing the instrument by plotting zero air mass extrapolation for the simple F naught, there's no reason why we can't pull out one more parameter that tells us about how it's going to fall off. A lot of the stray light is probably coming from the grading, but there has never been a careful characterization of exactly what is the source of the internal stray light. This is not a very good set of observations, but it clearly shows the difference between the double brewer number 119 holding up here with constant ozone right out to very large air masses, and this typical curving off that occurs because of stray light within the single instrument. We have done some modeling to look at whether the particular characterization function I'm proposing really makes sense, and it appears to be useful. The way I stumbled on it was simply to start fitting the data by different choices, trying different things, like let's try ozone path squared, let's try ozone path cubed, or something like that in a spreadsheet. And it was clear that we could come up with a function that fit that fall off very nicely. This is just the corresponding modeling of a double brewer compared to the fall off on a single. So if we're going to handle the stray light issue, traditionally we basically just calibrated by fitting this little part of the curve and extrapolating through to the extraterrestrial at zero air mass. What we're doing now is adding in another parameter that will represent the curvature as this falls off at large ozone amounts. And this is the function. It looks similar to the original simple Langley example. We have an F0 and we have the path length of ozone represented here. But we also have a correction factor here that handles large air mass. The reason it has air mass here and air mass -1 here is that actually fits the data a little better. But we're keeping air mass as a multiplicative factor so that the F0 that you get from the nonlinear form will be more easily understood in relationship to the F0 from the original Langley function. So then you do a lot of mathematics here and do a nonlinear least squares fit to find the F0 given the ozone cross-section and find gamma. And also, sometimes there are errors in ozone because of the results of changes in the color of the neutral density filter. So it's possible to put in a comb function here that is 1 if it's filter 0 and 0 for the others, and so on. A vector with a 1 in the right position for each filter, and then put in an intervention here that accounts for the fact that the points don't all line up with the minimum square error. So having done that, we actually ran some data through it. We've got quite a few rather better examples than this one, but I haven't put them into a slideshow yet. So these are the things that we're including: the filter change, the nonlinear factor, the column ozone amount, and the extraterrestrial constant. You can actually include multiple days in the analysis by just retrieving a different ozone for each day. And the other factors should be the same if the instrument has any hope of being stable. One of the things that comes out right away is that there is going to be a maximum here, and the modeling clearly shows that it falls off again, and some of the observations show that as well. So you've got a problem. If you get out here beyond that maximum in absorption, then you've got a double-valued function, and you don't know whether to start looking for a solution on this side or looking for one on that side. So you actually have to take this analyzed maximum ozone slant column together with the climatology of the maximum ozone over the station, and then dictate a maximum air mass so that you never get into the double value situation. Now, we ran some data from the double through the algorithm, and we also ran data from the single through the algorithm. And indeed, the stray light factor is about an order of magnitude smaller in the double brewer. My guess is that that's not exactly stray light. It's probably something to do with the atmosphere, maybe the finite slit width. But it does straighten out the double brewer data just a tiny bit by putting in a very small value for that factor that accounts for nonlinear absorption. So I hope that that will come out fairly soon. My student has been working very hard on it, and I just put a monkey wrench into her work by getting her to go back and start over again and put dead time errors into the retrieval as well, because you can see in some cases that a filter change should be just a jump in the absorption function. But if you see a jump that then goes away, it means that the dead time is the problem. And so we're just experimenting to see whether we can actually retrieve all of those effects at once to make a global data set of a number of days of data taken at Mauna Loa with the one instrument. Okay, these are some of the people that helped me survive to do the things that we're doing. And in particular, my travel to this meeting has kindly been provided by Kip and Zona. Thank you very much. Are there any questions? Yes. Yeah, I mean, we've been doing that. We've also been doing ensemble retrievals where the factors that are associated with the instrument stay fixed for all days, but the ozone changes on each half day, right? And it's coming along. We need to just get the final thing done with really good data, and that's what Zara is working on right now, trying to get it really polished up for publication. Well, yeah, I mean, it is going to take some work, but basically, it's the same problem we have in general, because you have to fit the instrument absolute calibration data in Mauna Loa, and then you have to propagate it through the system. It's the same issue that I talked about earlier. If we change the ozone cross sections, we're going to have to do all that. So I think we want to be trying to get this in order for 2 years from now. When we want to change the cross sections, we can do the whole thing at once and not be doing 3 iterations to try and sort it out. And what we're doing right now is to try and understand the efficacy of the thing, is to actually do some long-term trend assessments of Arctic stations that have changed from singles to doubles, and see whether the inclusion of this actually is a visible correction to the long-term trends. And that's the thing that I think will be quite exciting, to actually see the impact, you know, in the month or two, spring and fall, when you have really long air masses. Right? Okay. And I guess one point I'd like to make about this is that though it's a simple parameterization, I think it's rigorous, because it's essentially doing the same thing that we're already doing with the Langley analysis. Now, we did look at 2 different instruments, and one of them had a gamma that was about 1.2 in 10 to the minus 6 or something. The other one had a gamma of about 1.4. So we've already got some hint that if we used an average value there, it would be worth correcting any instrument to that extent. And we just need to look a little deeper and see how accurate that really is as an estimate by looking at more instruments. Okay. Any other comments? Okay, thank you very much.